Here's a very good and basic u substitution problem. We need to decide what will be a good u to simplify the integrand. And I said before, the best thing to do is see what stuff we can cover up, like what would be an easy inside, and we don't want it to be too big. So if you take the whole denominator, when you differentiate this, you have another chain rule, right? Because this is all to the half, and then you have 1/2 times the stuff, times 5 because of the chain rule. So that's a little much. We don't also have another radical to deal with in the integrand. So we want to pick something that's just big enough. It also has its own derivative in the integrand. So let's choose as u just 5x plus 8. The derivative then of 5x plus 8 is 5 dx. And you can see in the integrand we have dx, but we don't have the 5. So to adjust for this, we can say, well, if du equals 5 dx, then what we have is dx in the integrand, and that is 1/5 of du. And then the substitution looks like this. We've converted the indefinite integral to 1 over the square root of u times what was dx is 1/5 of du. And then we can clean it out. Remember, like, the 1/5 is a constant, so it can come outside the indefinite integral of 1 over the square root of u with respect to u. And probably we want to rewrite the square root as to the -1/2 power, so that would be 1/5 u to the -1/2 with respect to u. Then finally find the antiderivative. So the 1/5 is around for the ride. He's still there. U to the -1/2 goes up 1 power, and we divide by that sum, -1/2 plus 1. -1/2 plus 1 is a positive half. So both of these guys are a positive half value. That means we have 1/5 times u to the 1/2 divided by 1/2, or multiplied by 2 over 1. So the antiderivative is 2/5 u to the 1/2. We can't leave it that way though. The problem was presented in x land. We turned into u land. Let's go back to x, resubstitute, return to the original variable. So we have 2/5 times x, which is 5x plus 8. Remember, that's the bridge between u and x. All raised to the 1/2 power, and plus c, because this is a general antiderivative. (20) again is a pretty straightforward u substitution problem. As soon as you see the two instances of the variable, you say, "Ay caramba, something has to be u, so what could it be?" We want to choose the thing that has its derivative in the integrand. So you might say, well, I have a y squared here. If I take the derivative of y squared, I get some kind of y to the 1. So maybe this is some part of my u, and this thing should be part of my du. And let's flesh that out a little better than this in theory business, and say, let's have u be all that stuff under the radical. 7 minus 3y squared. Then the derivative of u, the derivative of this equation is derivative of 7, 0, times -6y with respect to y. So we have 3y dy, but our du is -6y dy. What we want to do is solve this equation for what we have in the integrand, y dy, which means that du is -1/6. Or -1/6 times du is equal to y dy, which is what we have, this y and that dy. I found like just ignoring the 3 is a little bit easier for students at first, so we'll just like pull the 3 out, if you will, and say that we have the square root of u times y dy is -1/6 times du. Then we can clean this up. -1/6 times -3 turns out to be -1/2 times the indefinite integral of the square root of u with respect to u, which we rewrite probably as negative 1/2 the indefinite integral of u to the positive half with respect to u, and then find the antiderivative of this, so the negative 1/2 is a constant, times u to the 1/2 plus 1 divided by 1/2 plus 1. Cook up these values. 1/2 plus 1 is 3/2. It's also 3/2 down here. That's negative 1/2 u to the 3/2. And instead of dividing by 3/2, let's multiply by 2/3. Then we can say that the 2's cancel, and we have just negative 1/3 u to the 3/2. And we're not finished yet. Remember, we have to convert back to x's and substitute that, so the antiderivative in terms of x's is negative 1/3 x, or excuse me, y, we're going back to y, 7 minus 3y squared to the 3/2 and plus c. Always, you can check. Make sure we found the correct antiderivative. That's negative 1/3 times the exponent 3/2 times 7 minus 3y squared to the 3/2 minus 1 is 1/2. And then by the chain rule, the derivative of the inside is negative 6y. The 3's cancel, and 6 divided by 2 is a 3. And the negative make a positive. So here we have 3y times 7 minus 3y squared to the 1/2. Exactly the same as the integrand we were trying to find the antiderivative for. So we did a good job. We made a correct selection, substitution, and antidifferentiation. So everybody loves trig, and trig is a great thing to use substitution for because trigonometric functions have arguments, and arguments are beautiful, beautiful choices for u. For example, this u is 3z plus 4, and the derivative of that u is the derivative of 3z plus 4, which is 3 with respect to z. So if we make the substitution, here's u, and dz is there, but we don't have a direct substitution. So what we've done before is said, well, dz, what we do have is equal to 1/3 du. And we can substitute that in there. So we have the indefinite integral of the cosine of u times dz, which is 1/3 the derivative of u. We can rewrite this, let the 1/3 hang out front. The indefinite integral of the cosine of u with respect to u, then find the antiderivative. What function has a derivative that is cosine? The answer is the sine of u. 1/3 is still along for the ride, he's just a constant, and we return to z land to write our final answer and add the c. So 1/3 the sine of z in terms of u is 3z plus 4 plus c. So we found the antiderivative with u substitution for this integrand.